Okay, I think we're on. So, Ji Young received a master's degree in applied mathematics from Hanyang University. And since September 2019, she's a PhD candidate at the School of Electrical Engineering of the Korea Advanced Institute of Science and Technology, KAIST. Her research interests include quantum information theory and network quantum information theory. Let's all welcome our speaker.
Thank you for introducing me. Hello, I'm Ji Young from KAIST in South Korea. Today, I'm gonna present non-local network coding in interference channels. My supervisor is Professor Junwoo Bae, and my collaborator is Professor Ashutosh Rai. So before starting the talk, I wanna introduce my lab. So they are my lab mates, and then we are studying quantum information theory, and the research fields are fundamental of quantum theory and then quantum computing and network and so on. So here, me and Ashu and Professor Junwoo Bae, we are working on network information theory with quantum resource. So today, I will present from the motivation of the quantum network information theory, and then I'm gonna explain background of the network information theory and the non-locality that used in network as a resource. Then to introduce the scenario that we considered in this work, and there are three main results. First, general framework with interference channels, and we show the advantage of non-local and quantum coding. And lastly, I'd like to suggest the optimal network encoding scheme. So anytime you can interrupt me, and then please ask me like if you have any questions. So as you know, in classical communication, several senders and several receivers share a common network channel, and each sender is influenced by the other sender's message. So we call it as interference, and we want to consider when several senders can share quantum or non-local resource and exploit them as a cooperation. So there are various types of network protocol, but first, the multiple access channel is multiple senders communicate with a single receiver over a common channel. And then like these M stations, like wanna send a signal to a single satellite, then we call it multiple access channel. And then also here there are two sender and then two receiver communication system, and we call it interference channel, which means the signal from each each senders wish to send a signal to the respective receiver, but each receiver can suffer from the interference from the other transmitted signal, then we call it interference channel. So in these network protocols, we're gonna use non-classical correlation, that is entanglement and non-locality, to enhance the efficiency of the channel. So when there are multiple senders like multiple access channel and then interference channels, we will consider several senders share entanglement and non-local correlation as a resource. So these interference channel and multiple access channels are fundamental model in network information theory, and we make use of entanglement and non-locality as a resource in these network channels. So we are developing the quantum network information theory to understand the possibilities or limits of the quantum resource in communication network. So on these topics, we already published a paper in 2020, non-local network coding in interference channels. And a few months ago, we uploaded the local and quantum advantage in network coding for multiple access channel in archive. Today, I'm gonna talk about this non-local network coding in interference channels. So let me introduce the interference channels model first. So here there are two sender and two receiver communication model. And then two sender Alice and Bob cannot communicate each other. And then choose message M1 and M2 and then send them to Charlie. And then Bob want to send a message to Dave. Then encoding E maps message M1, M2 to the X1, X2, the code words of that channel, and then decoding finds the message from the resulting sequence of the channel. So interference channel generally described by conditional probability Pn, y1, y2 given x1, x2, and rate R1, R2 is achievable if the average probability of error converges to 0. So here we can define the capacity region. So the capacity region C corresponds to the closure of achievable rates. So in my research, we are interested in some capacity defined as a maximum of some rate R1 plus R2 for achievable rate pair R1, R2. And then we're gonna use non-local resource in our network protocol. So I wanna introduce this very simple Bell scenario and then what we used in the network protocol. So let me explain the node signaling and then local quantum in CHSH game. So we can consider the simple Bell scenario. Alice and Bob spatially separated and then cannot communicate with each other. The inputs X and Y are measurement setting, and there are corresponding outcomes A and B. Then after repeating the experiment many times, Alice and Bob estimate the conditional probability PAB given XY. So we can consider the game, which is the winning strategy, is the sum of the outcomes of measurement is equal to the product of two inputs, that is the XY equal to A plus B. Then Alice and Bob win and then get +1. Otherwise, if the XY is not equal to the A plus B, then referee wins, and then Alice and Bob get -1 score. Then this X and Y, the measurement setting can be prepared 0, 0, 0, 1, 1, 0, 1, 1 with the probability 1/4 each. And then XY, the product of XY, it will be the 0, 0, 0, 1. Then we can calculate the winning probability here with this winning table. Then now we can define the value of the CHSH. It can be calculated the winning strategy with the winning probability. They will get the 1 score, and then with the probability, the lose probability, they will get the -1. So we can calculate this one. So we're gonna calculate this CHSH value with these 3 correlation. So first, no signaling correlations are characterized by this linear constraint. Then here the outcomes B does not depend on the LS measurement setting X, and then A also does not depend on the Bob's measurement setting Y, then with this no signaling correlation, we can get the CHSH value up to 4. And then local correlations can be defined when two sender can share the randomness lambda. And it can be written by the convex combination of deterministic points. This deterministic point is the local response to the input X and the shared randomness lambda. So with this local correlation, we can calculate the CHSH value up to 2. And lastly, quantum correlation is when the Alice and Bob can share the entangled state. Then we can use the conditional probability that are compatible with quantum theory. So for some quantum state law AB and the measurement pi AX and pi YB, we can use the following correlation. Then with this quantum correlation, we can get the CHSH value up to 2 root 2. So now we're gonna use these 3 correlation in our network, the interference channels. So there is one previous result by Quick and Shore in 2017. So let me introduce this one first. So in 2017, they provided very specific channels based on CHSH game. So these X11, X12, X21, X22, they are the input of the channel. And then here are the output of the channel. So there are 4 inputs and then 2 outcomes of the channel. So these gray parts are the winning strategy of a CHSH game. So you can see here, if X12 plus X22, we can, if we look this part, then X12 plus X22 will be 0, and then X11 and X21 will be 0. So it's equal, then this part is winning strategy, then there is noiseless channel. Just the first bit of this one, and then first bit of this one will be to the output of the channel. So similarly, this part also the winning strategy of CHSH value, and then the first bit of 0 will go to here, and then first bit 0 will go to the here. So similarly, this one also the here, okay. So this part also winning strategy of CHSH game, then this first bit will go to here, the first here, and then this first bit will go to here. So otherwise, if the white color is meaning the not winning strategy, then it will go flipped, exactly flipped. So this first bit 0 will be flipped to 1, and this first bit will be flipped to 1, like this. Okay, so they considered a very specific channel like this, and then they showed with this channel some capacity with no signaling strategy. The no signaling strategy is 2, and then they showed some capacity with local correlation is equal to 1. So they conclude that some capacity with no signaling strategy is greater than the capacity with classical and quantum strategy. So they showed this part with channel 1. So now I wanna introduce my scenario. So here it is. So we defined cooperation assisted channel. So here omega denotes the cooperation mapping from U1 to X1. And then here we use the resource, local or quantum or no signaling. So we assume that these shared resources are memoryless. And then now we can find the objective function of our work. This one is the maximum of sum rate over all possible cooperation strategy omega. So we exploit the local quantum or no signaling correlation for cooperation strategy. And since all these three sets are convex, and the sum rate is convex function of cooperation strategy omega, then we can calculate the sum capacity. Only we need to consider the extreme element in the set of cooperation strategy. So from here, is there any question?
Yes. Could you go back from the previous slide?
Okay.
So if I remember, you have M1 and M2, and then M1 is going to do, they both are going to do some kind of encoding, but M1 wants to send a bit to M1 hat, and M2 wants to send a bit to M2 hat, right? And then when they're going to use this channel, there's some kind of interference that can happen, or perhaps as some bits can be flipped. And this table is just going to tell all the possible outcomes for this 2-bit scenario, correct?
Yeah, right.
Okay. I think the part that I'm kind of lost here is how exactly are you using these correlations? Because I understand that if you are in a no signaling scenario or quantum or local, this is going to change how the probabilities are going to be considered. But here that you're just going to try to send one bit to M1 and one bit to M2, how exactly these different scenarios are going to help? Like, what is the effect of the scenarios?
So here, so this part could be interpreted like this here. Can you see my mouse?
Yes.
Yes. Then when they prepare the M1, M2, they use the correlation in the encoding part. So if they use the PR box in encoding, then they will get some output of the PR box like this, right? So if we can think about this XY is the M1 and M2, then we can get some A and B from the PR box, right? Then we will prepare after the encoding, the first bit will be just message M1, and then the second bit is just output of the PR box. So we will prepare XA like this. And this part, the same way, we will prepare the first part is just exactly same, the M2, and then this X2 part is the output of the PR box B. So if we prepare XA and YB like this, then it always go this gray part, then they can show this no signaling capacity is 2. Did you get it?
Yeah, but I mean, I think what I didn't got is
Uh-huh.
that is the task just to send one like 2 bits, right? 1 bit from M1 from hat and another bit to M2 and M2 hat.
Yes.
And the channel capacity is going to. Okay.
Question.
No.
So I just wondering, could you remind me again, like this interference channel? So we consider this like quantum or PR scenario to improve what? Like the I'm not like maybe I'm not clear. Like this interference channel would mess up the messages. So we want to use this correlation to improve. Like,
Yes.
well, what does this channel do? Is my question clear?
I'm sorry. So what is your question? So we wanna use correlation in these interference channels, and then.
Yeah, I think that his question is kind of like the question that I was asking as well. It's like what exactly is the role of this correlations in the channel? Like in this case, they're just studying like all the different possible types of correlation, but how is this going to influence the outcome?
Okay.
It's maybe more like in the previous step, like this interference channel, like what is it bad? Like it's noisy, or I don't know what is that channel. So and I'm not sure like why you consider this correlation to improve what.
Okay. So interference channels means M1 should be go to here, M1 hat, and then M2 should be go to M2 hat. But the definition of interference channel is the mutual information of M1 and M2. If that is not equal to 0, then we say interference channel. It means it's influenced by the message M1. So, right? So we wanna use the correlation to dealing with this problem. So there is some the limit when we use the Shannon local theory in the encoding scheme, then we can calculate some capacity limit. But when we use the non-local resource in encoding scheme, then we can show there is gap between the Shannon limit and with the quantum resource. So so we considered very specific channels that can show the gap between the Shannon limit and then quantum resource. So this channel looks like very specific because it depends on the CHSH game. So if the 4 bits are in the CHS, the winning strategy of a CHS game, then it will go noiseless channel. And then if 4 bits of channels are not in the winning strategy, then it will be split. So we define very specific channel. Then it will depends on how we can prepare the code word here, right?
Okay.
So
Okay.
So basically, you don't want like M1 to like the M2 height has some information from M1, so you try to using some encoding to like use the same channel but separate the message. Is that correct?
Okay. Yeah. Right.
Okay. So I have another question is, so usually in the Bell scenario, you have to repeat the experiment many times to calculate the correlation, but
Yeah.
here you only do once, or you have to sample several times.
So if we think like practical model, then we have to do the many times. We have to do to get that correlation.
Okay, but
Yes.
like for sending one message for one M1, so I already need to do it many times. Correct?
Yeah, right. So given M1, M2, we will do Bayes experiment many times, and then we can get some output of the that Bayes experiment. Then we will use the input and then output, and then making some code word from that input and output.
Okay, thank you.
Okay. So from now on, I wanna introduce the new work in this field. So we define the new channel here, the given channel, and then cooperation channel. So we will call it cooperation assisted channel. So this cooperation mapping means like we can use the results, the local, quantum, or signaling here. So we can get some code word X1 from the U1. So we will calculate the sum capacity of here, the sum capacity of cooperation assisted channel. Then it will be calculated by the sum of mutual information U1 and Y1 plus and the mutual information of U2 and Y2. So using this lemma, the sum rate is convex function of cooperation strategy omega, and then the sum capacity corresponds to the maximum sum rate over extreme element in the set of cooperation strategy. So from now on, we can consider the extreme element in each resource set. Okay. So we considered like for input and for output channels. And then here we consider the cooperation function of from the U1, U2 to X1, X2. Because of our channel is should be prepared by for input. So we want to consider 2 for Bell scenario. So we call it Collins, Jisan, Linden, Massar, Popescu scenario when the D equal to 4. So here we want to consider given U1, U2, X1, X2 could be the 0, 1, 2, 3. And then if X1 equal to 0, it means the input of the channel Xi1 and Xi2 will be prepared by 0, 0. And then if Xi equal to 1, then input of the channel will be prepared 0, 1, and so on. So we wanna consider all the possible cooperation strategies. We use the local reversible relabeling for this 2 for Bell scenario. So we can think like for Alice part, we can prepare this U1. So we need to think like permutation to input new one, and then here like a given input to U1 equal to 0, we have to think about the permutation to output X1, and then also we should consider the given U1 equal to 1, we should think about the permutation to output X. 1. So at least parts, the local reversible relabelings, the number of local reversible relabeling is like this: 2 permutation times 4 permutation times and 4 permutation. And then both parts also same. That's why the total number of local reversible relabeling functions is like this one. So to compute the sum rates of cooperation-assisted channel, we use the geometry of set of local quantum low signaling correlation, and then local sum capacity. So local correlation can be defined like this. We already saw before. And then local sum capacity correspond to the maximum sum rates over all extreme elements in the set of local encoding schemes. We only need to consider the local extreme point here. And with this point, we will calculate the sum capacity, and then we will find what is the maximum of the sum capacity with local resource. Then we need to find all these extreme vertices. Then it could be get from these local representative vertices, and then we will do the local reversible relabeling of these representative local deterministic vertices. Then we will get 256 elements. Then from now on, we don't need to think about like all these sets. We only need to think about these 256 elements to calculate the local capacity. Similarly, like no signaling correlation also polytope, so we can find all the vertices of no signaling sets. So using this two-fold scenario, no signaling representative vertices, also we will use local reversible relabeling, and then we can see when the k equal to 2, maybe I think there is some loss of information.
Sorry, what happened?
Yeah, I think I didn't write this. So it should be like half and 1/3 and 1/4, like this.
Okay.
So for each k equal to 2, 3, 4, we can find all the extreme element, and then we will consider all the signaling vertices, and then calculate the sum rate, and then we will find what is the maximum of the sum rate. Then we can show the sum capacity here also. But the problem is the quantum set, because quantum set is not polytope, and then it's still hard to characterize. So we approximate the quantum capacity. So we derive the lower and upper bound. So first, for lower bound, we generate the quantum strategy from Bell experiment. So we exploit the maximally entangled state psi, and then using this measurement, we got the Tristan correlation that gives the maximum value of CHSH inequality. And then we found all possible mapping by local reversible relabeling, and then some rate is calculated for all these in the corporation. And for upper bound, we construct the new polytope that containing quantum set and still in the no signaling set. So we found some vertices that giving the maximum sum rate with no signaling cooperation. So we removed that part, and then prove that this new polytope is containing quantum sets using NPA hierarchy. Then we got the upper bound of quantum capacity by calculating the sum rate over all the extreme points of new polytope. So that was the methodology to calculate to show the gap between the resources. And then from now on, I will say the main result. So firstly, we define general framework with interference channels. So we considered an extreme channel here. So there are 4 inputs of channel: x11, x12, x21, and x22. And then the first bit could go like with noiseless channel or like with the bit split, and second bit also go to the with the noiseless channel and then go to with the bit split channel. So here we define the extremer channel. K00 means there is noiseless, and K0 means is x11 will go noiseless, and then x21 will be flipped like this, and then K10 means x11 will be flipped, and then x21 will go noiseless, and K11 means both x11 and x21 will be flipped. So with this extremer channel, we can define very general probabilistic mixture for extreme channels like this. So from now on, we say this channel vector P00, P01, P10, P11. So P00 means there is noiseless channel, and P10 means with probability P10, the first bit will be split. I'm sorry, the second bit will this one, the x21 will be split, and then P10 means the x11 will be split, and then P11 means both the probability of both bits split. So with this channel vector, we can define the channel depends on if the channel inputs are in winning strategy of non-local game or not. Oh, okay. So from now on, I will consider the channel depends on the CHSH game. So if the 4 inputs are in the CHSH game, then we can define some channel vector, and then otherwise we can define the other channel vector. So here we saw the Quick and Sure 2017 paper. We can write P winning probability vector is 1, 0, 0, 0. So when the 4 bits, the input of the channel are in winning strategies, then it will go the noiseless channel with probability 1. And then if 4 bits of 4 input of the channel are not in the winning strategy, then if the both bits are flipped with probability 1. So similarly, in 2020, in our paper, we also defined the channel looks like this. We generalized from the Quick and Sure's paper, but from now on, we generalized from this 2020 papers. We considered all possible live channel. So investigated 5 classes of channel. So I'm sorry, there should be the channel 1 here. So for channel 1, 2, 3, we found the no signaling resource. Means here the red color, it means the no signaling some capacity. So we found the no signaling resource are strictly more useful than quantum ones, because this green one is the upper bound of the quantum capacity. So we can show the strictly more useful than quantum one. In the same time, for the channel 1 and 2, local correlations are all as helpful as quantum ones for small value of an error parameter eta. And then for channels of 4 and 5, the sum capacity with no signaling correlation is strictly away from the maximum value too. So from here, non-local and quantum advantage are shown. Capacity with no signaling correlation is strictly higher than an upper bound of capacity with quantum resource, and lower bound of capacity with quantum resource is strictly higher than a capacity with local resource. So we show the advantage of a non-local quantum coding here. And then here we consider the practical model. So we found the suboptimal network including cooperation when we want to use non-maximally entangled state. So in real world, it's hard to prepare maximally entangled state. Then we can share non-maximally entangled state. Then we want to use that one in the network protocol. Then we can think this method. So first, two senders do the bell test, and then check if they share the non-local resource or not. And then senders transform it to the isotropic correlation using rearrangement and then local randomization. Then we can use these two suboptimal encoding. So, so before we had to consider all possible of the encoding scheme and then calculate the maximum sum rate for quantum resource. But from now on, we can just consider these two suboptimal network coding. So I brought one very simple example. So for this channel, when the four inputs are in winning strategies, then there is noiseless. And when four inputs are not in the winning strategies, then it will go noiseless channel with probability 4 and 5, and then it will be both bits are split with the probability 1 and 5. Then when we use this suboptimal cooperation strategy, then we can calculate this graph. So this red one is the local sum capacity, and then when we use the isotropic correlation, we can get this green line. So this epsilon meaning is here, the parameter of the isotropic correlation. So if the epsilon is greater than the 0.20248 and then less than the 0.414, then we can say the non-local resource enhance the channel capacity. So if epsilon is greater than 0, then two senders share non-local resource. And then when epsilon is greater than 1.414, then two senders share like above the quantum resource. So we say super quantum resource. So we only consider this red part. So in conclusion, in this work, we made a general framework with interference channel, and we showed the advantage of non-local and quantum coding, and then suggested suboptimal network operation strategy to any non-local network coding. So this, here now it was my presentation, and then thank you for listening. And then if you have any questions, please, yes, ask me, please.
Okay, thank you very much for your presentation. So it's open for questions. The audience has. I think we have one here.
So I just wondering, like, how the so this interference channel is to try to see, like, we have two sender and two receivers. So like Alice was sent to Charlie and Bob was sent to Debbie, like they separately, and how this capacity, like channel capacity, related to how success this channel works. Like how do I know whether the message is sent to them separately?
How to messages sent separately? How
yeah.
to?
Like, yeah, like you talk about like this channel capacity. So, but I don't know like how this capacity related to the task itself.
So we consider the sum capacity written here. We calculated only the mutual information of U1 and Y1, and then plus and mutual information of U2 and Y2. But it's not we didn't consider all the capacity written. We only considered some capacity written here. So we can calculate just using the mutual information of U1 and Y1.
Okay. So then there is a threshold, means that, okay, like above this, then they so like the like there's no mutual information between how to no like, so I mean like some threshold, then I know, okay, this message is sending separately to their to who will receive.
I mean, you mentioned, I think, a few slides after this, that depending on a certain vector, in the CHSH game, then the channel would act like the identity, right? So there would be no error, or like no mixed signals.
Yeah.
Well, I guess his question is like, if you have the scenario, then you're going to maximize this mutual information between sender and receiver, right? So that would be kind of the relation between the capacity and these different strategies for the channel. I think that's it.
Maybe I didn't think that much. I guess.
Yeah. So we define the interference channel here, PN. So it could has like error or not with the channel parameter.
Yes, exactly.
And then like we define the cooperation assisted channel with this cooperation. So cooperations could be the local quantum node signaling, and then we calculate of the sum rate to who this new channel. So we calculate the major information of U1 and Y1, and plus U2 and Y2.
But then would be fair to say that you have this parameter P, right? That is going to be associated with the errors. And if you have a parameter that gets no errors, that would be equivalent to saying that the capacity is going to be higher. I think that's kind of the answer. The
Oh,
question.
yeah, you're right. So if this channel, like depending on how we define the channel, depends on the like if the inputs are in the winning strategy of CHH game, then noiseless. Then it's
Yeah.
really depends on our like operation.
Mhm.
Do you mean this one, right?
Okay, I think we have another question from Hayato.
Okay.
Yes, thank you. So I understand. So you gave many statements about the superquantum performance of no signaling boxes, but I cannot catch up the motivation of your talk. So your motivation is only foundation of quantum correlation or others? Which one? Did you aim to characterize the quantum correlation, or did you aim something?
So, oh, I'm sorry, but can you ask me one more time, please? I'm really sorry.
So my question is, what is the motivation of your studies?
Motivation of study.
So yeah. So I understand the no signaling box has a superquantum performance of such a
Okay.
communication tasks. So what is a statement? Your statement about your study?
So I wanna consider the local set and then quantum set and low signaling set in the cooperation of the channel, right? And
Yes.
but quantum set is still hard to characterize.
Yes, I understand.
So we drive the lower bound quantum capacity and then upper bound. So to make this upper bound, we made a new polytope here.
Yes.
So we characterized the quantum lower and upper set. And then we used that one in the network coding theorem, network coding. That is the motivation. So we made a, yeah.
I understand. So, and I want to ask another question. So please go to the page 25 or something like that. So there are 4 graphs.
Yeah.
4 or 5 graphs. Yes, this one. So this is also this is very interesting mathematically. So for example, the center graph is completely separated to the any cases, but other graph does not completely separated. So did you have any condition for such complete separation or something like that?
It's really, I don't know, because it depends on how we define the channel, but still we cannot like analysis all parameter of channel. So we still have some example like this, and then we can show for some channel there is advantage, but we cannot say like analytically like for all the channels.
Yes, but maybe my question depends on the boundary of the each correlation, I think. So it is important for your motivation, I think. So what do you think?
Yeah, let me think about it, but yeah, still I don't know about it.
Okay, thank you so much.
Thank you.
Okay, we have a question here.
Just simple question. So, can you explain all these probability vector PW, PL or something, all these PN or W, are they given or they are different corresponding to different cases? I do not know the setting.
Yes, this PW and PL means the so PW means if the for input of the channel in the winning strategy, then we can define the channel vector like this. So P00 meaning there is noiseless channel, and P01, I think it would be better. So P01 will be the second bit will be split, like this second bit will be split, and then P10 means the first bit, this X11 bit will be split, and then P11 means this X11, X21 both are split. Okay, then from here, like PW equal to 1000, meaning when the four inputs of channel are in the winning strategy, then always noiseless channel, and then four inputs are not in the winning strategy, then it will go noiseless channel with probability eta, and then both bits are split with probability 1 minus eta. So we can read the channel vector like this. So we investigated the 5 different classes of channel. So it's so this like channel 4 and 5 we considered like if there is like losing strategy, then like there are mixture of all possible channel, and then I think you can read the channel vector like this. Then is it your question, right?
Meaning of, so okay, so I mean you basically define the element for each probability vector, but you are investing here different channels and with different probability with your own definition, and you try to see is there any gap between the winning and losing probability. Yeah, I mean you are basically discussing different channels. Yeah, I understand. Okay.
Yeah, okay. There is no connection between the channel. We just select from like our previous paper, and then we consider some Ladinsky. They have some paper. They studied the Mac channel, so we derived the channel 4 and 5 from the Ladinsky paper. So we consider several channels.
Okay. And sorry, final question. In your last few slides, you mentioned the extremal channel or extremal, right? So are they just corresponding to the corner of different polar of the polar top, or what's the extremal channel you have? Oh, why you call it? Yeah, call it extremal channel.
Oh, extremal channel means just K00 is there's noiseless channel, right? And K01 meaning only this F21 will be split.
Okay.
And
okay.
yeah, so we will use this for extremal channel here like this, like Probably
Okay,
it's a
so
mixture of for extreme channel.
okay, I see. Okay, each one correspond to a separate channel. And
Yeah, right.
Okay, okay, good. Okay, thank you.
Thank you.
Perhaps just a final thing, a final question for me. And it's because of Hayato's question. On the next slide, you have the channel 3 that indeed has like this kind of different properties because you have this plane separation between the non-signaling correlation and the quantum local. And I think my question is, how did you arrive to this channel? Like, how do you think about this channel or this
How
this
do I
value?
think about channel 3?
Yeah, it's like it came from somewhere, like.
It could be like, I think it's not that much important because if we can show some gap between these four, even here, it's the same. I mean, because this eta parameter is just so we can get some capacity given eta. Did you get my point?
Because you can get the some capacity given eta.
Yeah.
Okay, so perhaps the point is that perhaps this distinction is not that much important. What's important is that you get the actual separations.
Yes, right.
Okay. So I think we don't have any more questions.
Okay.
I would like to thank you again for coming here and giving us a talk. So
thank you very much.
And let me stop the recording.